Good afternoon, dear colleagues. Today I present a study that is decided to one of the largest environmental problems of our time, the degradation and restoration of the ecosystems of the Aral region. This work reflects a long-term analysis of vegetation dynamics and the results of large-scale phytomelioration programs implemented in Central Asia. Our presentation title is Vegetation Cover as an Indicator of Degradation and Restoration of Ecosystems in the Aral Sea region. Let me start it. So, introduction: the Aral Sea crisis. The Aral Sea, once the world's fourth largest inland lake, has become a symbol of environmental disasters. Unsustainable irrigation during the Soviet era caused the lake to shrink dramatically, transforming fertile deltas and wetlands into saline deserts. This ecological crisis disrupted biodiversity, altered regional climate, and created severe socio-economic challenges, including public health problems and loss of livelihoods. Vegetation cover has emerged as a critical indicator of these transformations. Its decline reflects ecosystem collapse, while its recovery signals resilience and potential restoration. So, research, science, finance. Understanding vegetation dynamics in the Aral Sea basin provides crucial insights and regional and global environmental science. Vegetation cover is not only an ecological indicator but also a driver of restoration. Native plants stabilize soils, reduce erosions, and create niches for biodiversity. This study demonstrates how long-term remote sensing data combined with phytomelioration practices can provide evidence-based strategies for combating desertification and achieving sustainable land management in arid regions. Our research objectives: the study set three main objectives. First, to analyze long-term vegetation dynamics in the Aral Sea region from 1980 to 2024 using multi-temporal stellate data. Second, to assess the effectiveness of phytomelioration program with native drought-resistant species as Haloxylon, Atriplex, and Artemisia. Third, to evaluate the potential of ecosystems recovery and resilience, offering insights for sustainable restoration strategies in arid zones. Our methodology: so this study employed a remote sensing and GIS-based workflow at Texas vegetation cover change in the Aral Sea region from 1984 to 2024. Multiple temporal Landsat like TM, ETM, and OLI and Sentinel-2 MCI imagery were used to generate annual and seasonal composites after atmospheric correction and cloud masking. Vegetation indicates like NDVI, CA, VI, and fractional vegetation cover (VVC) were calculated to capture dynamics of greenness and canopy design and density. Land cover classes like halopathic shrubland, and Hibberka steppe bar saline for surface water were mapped using supervised random forest classification. Vegetation trends were quantified at pixel level and aggregated by ecological zone. To evaluate restoration effectiveness, intervention are from phytomelioration projects with native species like Haloxylon, Persium, Atriplex, Kansas, and Artemisia were compared to degraded controls. Validation relied on published reports and monitoring data, ensuring consistency while acknowledging the absence of new fieldwork. And all analyses were implemented in Google Earth Engine and cross check in GIS problem platforms to ensure reproducibility. So our results: vegetation dynamics. Satellite analysis of the Aral Sea region 1980 2024 revealed dramatic changes in vegetation cover. Vegetation area from 45,000 square kilometer in 1980 to 80,000 square kilometer in 2010, followed by plateau recovered to 24,000 square kilometers in 2024. Spatial richness declined from 120 to 85 species, then increased to 90 in recent years. This recovery coincides with large-scale restoration programs, yet the ecosystems has not regained pre-degradation diversity. So you can see our restoration activities. We have 4 case studies how show to spatial effects. So area A, we plant sexual and automation for soil stabilization. Area B, we planted a triplex plus automation for improved soil and biodiversity. So area C, sexual and reed for reduced salinity. Area D, Artemisia and dandelion for dwarf residence. So you can see full our results in this table. The analysis identified dominant vegetation types and their adaptation to degraded condition in the Aral Sea basin. Haloptic communities, salsoil space triplexes dominate saline soils, demonstrating tolerance to high salinity. So saurophytic shrubs through in sandy areas, effectively stabilizing soils under extreme aridity. Synoptic steps like Artemisia and Po occupy transitional zone providing resilience to drought and soil erosion. Field-based monitoring confirmed the restoration area exhibited increased plant density, improved soil stabilization, and the creation of the new ecological niches. However, despite recovery species composition remain below pre-degradation levels, highlighting the need for continued efforts in biodiversity restoration. So this our research showed a table of sort changes in vegetation area in Aral Sea region from 1980 to 2024. So in this figure we can show dynamic vegetation cover in the Aral Sea in this period. So the graph illustrates the dynamics of the vegetation or RV changes in the Aral Sea region based on satellite from data 2080 to 2024. A sharp decline in vegetation between 1990 and 2000 as associated with ecosystems degradation caused by the reduction of water resource. However, in recent decades and gradual recovery of vegetation has been observed, indicating the positive effects of phytomelioration activity. As a result of the vegetation analysis in the Aral Sea region, the main vegetation types characteristic of various parts of the former Aral Sea but have been identified. These data provide a deeper understanding of ecosystem dynamics and the role of the different plant species in the restoration process. So, in conclusion, the findings contribution to scientific understanding by demonstrating that phytomelioration with native drug-resistant species like haloxylon, triplex, artemisia is effective in stabilizing soil and supporting vegetation recovery under extreme arid conditions. And the restoration dynamics can be reliably tracked using long-term remote sensing in combination with field-based data, enabling continuous monitoring at the regional scale. The recovery process remains incomplete and requires sustained ecological, socio-economical, and climatic evolution. In conclusion, this research highlights both of the progress achieved and the challenge that remain. It provides a scientific basis for guiding sustainable restoration of the Aral Sea region and for aligning national initiatives with global frameworks such as the United Nations Decade on Ecosystems Restoration 2021-2030. Thank you for your attention.